A laboratory experiment conducted by an international team of researchers has confirmed that X-rays emitted by a suitably sized atomic blast could shunt asteroids around 3 to 5 kilometers wide, around 2 to 3 miles, off their course. While there is no evidence of a pressing need for such an anti-doomsday device, the consequences of being blindsided by a hazardous near-Earth asteroid aren't trivial, making it vital to come up with a game plan that is guaranteed to save our skins. NASA recently demonstrated that if a heavy probe bumps a relatively petite pile of rock with enough force, it should steer clear of an impact with Earth. However, more data is needed before throwing chunks of metal at any old asteroid in the hopes it might avert disaster. There are more than one way to kick a mountain across the sky. Coupling it with a powerful fusion engine might work, or using a focused laser to create a rocket effect by ablating the asteroid's surface. Or, warming a small patch of an asteroid's surface with an intense glow of radiation could also create a rocket effect, vaporizing minerals with such ferocity the escaping gases could, in theory, push the mass just enough to alter its path. The basic principles behind evaporating rock with electromagnetic radiation can be tested and fine-tuned for different materials and mineral structures right here on Earth. Researchers used a high-frequency electromagnetic wave generator called the Z-pulsed power facility to squeeze 1.5 megajoules of X-rays out of a tank of argon gas. This bubble of radiation obliterated a thin piece of metal foil holding aloft a grain of fused silica, also known as quartz glass, leaving the sample hovering in freefall just long enough to resemble a tiny asteroid drifting through space. Austrian amateur astronomer Felix Schaffbanker has captured images of Pentagon craft that nobody knows much about. He used a 14-inch Dobsonian telescope to cross-reference the images with specs from various spy satellites launched by the Pentagon. Most of the recent sightings have been known crafts deployed by the National Reconnaissance Office, NRO, including the Boeing-built Future Image Architecture, FIA, radar satellites and some keyhole, KH-11 orbiters. However, one satellite stood out to Schaffbanker as nothing he's seen before. In the image, a strange 5-meter, or 16-foot, long panel was seen, while KH-11s don't appear to have such structures on them. A team led by Stevens professor Igor Pekovsky has proposed a method to detect individual gravitons, believed to be the quantum building blocks of gravity. They suggest that with advancements in quantum technology, this experiment could become a reality in the near future. The team, consisting of first-year graduate students Germain Tobar, Thomas Beitel, and postdoctoral researcher Srinath Manikandan, published their results on detecting single gravitons with quantum sensing in Nature Communications. Gravity is a fundamental force in our universe, with the classical version of gravity being the only known explanation for its existence. However, the quantum theory of gravity has long been a challenge to link gravity with quantum mechanics. In any quantum theory of gravity, we would expect certain single indivisible particles to occur. These elusive particles are called gravitons, and they are considered the building blocks of gravity, just as atoms are the building blocks of matter. In theory, the gravitational waves that frequently pass through Earth from colossal cosmic events like black hole collisions are made up of huge numbers of those gravitons. Impressive big detectors like LIGO can now confirm the existence of such gravitational waves. Yet a graviton has never been detected in history, even the idea of spotting one was long thought impossible. Pekovsky's team proposed a solution that involves coupling existing physical detection technology, an acoustic resonator, basically a heavy cylinder, with improved energy state detection methods, also known as quantum sensing. This solution is similar to the photoelectric effect that led Einstein to the quantum theory of light, just with gravitational waves replacing electromagnetic waves. The key is that energy is exchanged between the material and the waves only in discrete steps. Single gravitons are absorbed and emitted. To detect these gravitons, the team needs to cool the material and then monitor how the energy changes in a single step, which can be achieved through quantum sensing. By observing these quantum jumps in the material, we can deduce that a graviton was absorbed. One of the team's proposed innovations is to use available data from LIGO, a two-facility U.S. observatory that recently confirmed the existence of gravitational waves. The team's design for this experiment involved lots of math and creativity, along with some big help from recent advancements in technology. While quantum jumps have been observed in materials recently, not yet at the masses we need, but technology advances rapidly, and we have more ideas on how to make it easier. With some luck, one will be able to capture single gravitons soon.
Thanks for watching, like and subscribe.